Did you know that recently the UK has outlawed eating pineapples on pizza? Or that a woman murdered her roommate for sending her too many Candy Crush requests? Or that a certain virus from 5 years ago is spread through 5G signals? Now all of these are very clearly false, and if you were inclined to believe any of these, you probably need a lesson in media literacy and maybe a Reddit account, you goddamn neckbeard. Fake news is a plague. Different countries have their own ways of dealing with it, some more aggressively than others. While there isn't really a foolproof way to identify fake news and shut it down fast, there are ways that we can try. I mean, what other choice do we have? At this rate, old grandpa's gonna keep saying that our vaccines contain microchips controlled by Elon Musk. Just wait till he hears about cryostasis technology. This problem's not gonna get much better anytime soon, and with the recent news looking like it's straight out of a Family Guy episode, I think it's worth working on technologies to help identify and shut down fake news. So let's build a graph neural network to detect fake news. Before we begin, it would help to determine what exactly a graph is. This is a graph, but it's not the graph we're looking for. This is also a graph, but it's still not the right one. Now this is a graph. It's just a set of nodes that are connected by a set of edges. People have dedicated their entire lives to studying this for some damn reason, but it helps us represent interconnected things. Some examples include train systems, to-do lists, knowledge bases, the SCP archive, a life cycle of a butterfly, or even keeping track of all of the relationships on Love Island, which by the way is impossible for a regular human brain. As Dijkstra famously never said, everything is a graph. Kinda. We can represent a graph like this. One area stores what the vertices are, while one stores the relationships within them, otherwise known as the edges. Straightforward, right? Graphs can be directed or undirected. They can also be cyclical or acyclical, and weighted and unweighted. If you've been in the trenches of competitive programming like me, I'm so deeply sorry, but you probably recall these ideas. So you're probably wondering, what is the easiest way to represent this? Welcome to the adjacency table. An adjacency table is effectively a 2D array of ones and zeros, documenting the relationships between different nodes. So if node 1 points to node 3, the coordinate 1, 3 would be 1. If it's a two-way connection, both 1, 3 and 3, 1 would be 1. When you have weighted edges, the number can be increased accordingly to 2 or 3. So why is this useful? Let's say I wanted to go from Kuala Lumpur to Singapore. I could take a private jet all the way across the world together, or I could take a short bus ride. Of course, I am not Taylor Swift, so Google Maps would recommend me the faster option, which is the bus. It treats KL and SG as two nodes, and the edges connecting them as the different journeys with different weights representing the time taken. Therefore, by using the least weighted path, we can save time. So how does this link to ML? Well, ML techniques can be used on nodes, edges, or even entire graphs. For example, in a social media network, identifying Russian bots would be a node classification task, while detecting illegal conversations would be a graph classification task. You might be wondering, why not just chuck the whole adjacency matrix in the algorithm? Well, there's a big issue with that. Traditional ML is not permutation invariant, which means that the order of the input actually matters. But node 1 shouldn't be more or less important than node 5, just because we assign them random numbers. Thankfully, there are a couple of ways to handle this. This approach is still okay if we observe nodes individually. If the algorithm messes with the nodes, we need to record features of each node, such as the node in degree, node out degree, sum of outgoing weights, sum of incoming weights, distance to nearest neighbor, in degree of nearest neighbor, distance to root, and whether the node is part of a loop. Once the feature vector has been created, any standard ML model is ready for classification. Oh wait, but you do see some big downsides to this method, like the fact that the data has to be handcrafted, and that interrelationships between nodes are ignored. Back to the drawing board, I guess. It's fine, we're gonna be fine. Why did I even— Okay, let's take a different approach, using graph embeddings and node embeddings. An embedding is just a mathematical expression of a list of numbers. In language, words can have embeddings, where similar words end up close together. In graphs, nodes can have such embeddings too. So nodes that are related, like husband and wife, chicken and egg, or Singaporeans and free food, should end up close to each other mathematically. Embeddings are one way to represent graph nodes as numbers. Algorithms like Node2Vec learn these embeddings using random walks. But for this project, we are going one step further. Instead of learning these embeddings separately, we are using a GNN that learns directly from the graph through message passing. Every node starts with its own features. Then, each node receives information from its neighbors, combines it, and updates itself. After one round, the node knows about its direct neighbors. After 2 rounds, it knows about its neighbors of neighbors. And after 3 rounds, it's like the average high school reunion. For this project, each news article becomes one graph. The people spreading the article are nodes. Retweets, reposts, and shares are edges, and the features describe the articles and users. The specific model we are using is based on graph attention layers. A normal GNN collects information from neighboring nodes. A GAN does that too, but it also learns which neighbors deserve more attention. So if you had an old lady to your right who baked you pies every Sunday, and a serial killer to your left who threatened to rob you when you left for work, you wouldn't give them equal attention, would you? After message passing, every node has an updated embedding. But our final answer is not about one node, it's about the whole graph. So we use pooling to compress all of those node embeddings into one graph embedding, then a normal NN layer that turns that into a real or fake prediction. Okay, let's cut the theory before I start bleeding out of my ears. The plan is simple. Get a fake news dataset, turn it into a graph, give each node some useful features, train the model, and see whether it can classify news better than me staring suspiciously at a WhatsApp forward. First up, we have the dataset. Normally in machine learning, a training example might look like a row in a spreadsheet, but in a graph neural network, one training example can be an entire graph on its own. In this case, one example is one news article and the network of users who spread it. Okay, here are the imports we're gonna need. Of course, we're gonna be using PyTorch, my favorite ML library. UPFD, otherwise known as the User Preference Fake News Detection Dataset, is what we will be using to get our data from. Keep in mind, we won't actually be able to read the headlines or titles because they don't actually matter to us as much as the share patterns. Data Loader allows us to feed the graphs into the model in batches, and the last two modules help us draw the graphs. If I'm going to be burning midnight oil with cursed social media spiderwebs, I'd at least like to see them face to face. This cell actually loads our dataset. We check whether we can use CUDA, though I'm kinda lazy to set it up, and then we specify our training data and test data. Now, if we run this, it should give us our sweet mother of God. That's a lot of graphs. This specific line, which is printed as we asked for the first element, shows us the number of nodes, node features, classes, and edges. Y gives us the answers, and in this case, the article is real. When we all try to graph it out, we get this. Okay, not too shabby, I'd say. This converts our PyTorch geometric graph into a network X graph, which is exactly what this bacteria-looking guy is. So somewhere in this Smurf casserole, we have a bunch of fake news patterns. Knock knock, who's there? Data loaders! It's time to wrap up and ship off your data in batches of 1 to 8. We have to specify that shuffle equals true because we don't want the model to learn any weird patterns from the order of the data. The batch vector is the most interesting part of all of this. When you package all of the graphs together, it becomes one giant mega graph, and the only reason we can tell them apart is because the batch vector can separate them. Okay, let's put on our Tony Stark cosplays and actually build this thing. This model uses GATConv, which stands for Graph Attention Convolution. Okay, before we begin, a few things to note. GATConv is the graph attention layer. This is where message passing happens. Graph Max Pool is the pooling layer. This turns many node embeddings into one graph embedding. And linear is a normal neural network layer used at the end for just classification. Our model will have these three stages: passing, pooling, and prediction. I'll be explaining our convolution layers like a platoon of Girl Scouts selling cookies. In layer 1, we deliver cookies to our neighbors. In layer 2, we deliver them to their neighbors. And by layer 3, you've built a cookie empire of thousands of loyal customers. We define the linear layers. One processes the news or root node features, one processes the graph embedding, and the final layer combines both. This is the forward pass. The graph goes through 3 GAT layers where nodes collect information from their neighbors. Then, pooling compresses all node embeddings into one graph embedding. Then we grab the root node, which represents the article itself, and the sigmoid turns the final output into a probability. Look alive, everyone, our model's here. Let's just test it a little bit, and okay, one batch has cleared the model. Let's ramp things up one last time, shall we? Did you know allegedly 40 to 70% of elderly people fall prey to fake news? I've got a feeling our GNN can give old grandpa here a run for his inheritance money. This is what we'll be using for our training. BCE loss is binary cross entropy loss, which beats the model up for making wrong predictions. Our friend Adam is the optimizer. This is our training loop. We send in graphs, the model makes predictions, and then depending on those predictions, backpropagation adjusts the weights. This here is the test function. It does the exact same thing without training. Lo and behold, we have our last important piece of code, the simulator. One epoch is one full round of going through all of that training. Let's do 50. Well, it's improving, kinda. Jeez, this reminds me of my lower sec math grades. Okay, great. Looking at our training and test loss, this looks fine. And our training accuracy only seems to have gotten better over time. Take that, grandpa. This has been a journey. After several crash out sessions and a couple liters of Monster Energy, I've built a model that guesses fake news a whole lot better than your grandparents. Well, sure, my model can't bake me a pie on Sunday morning, but what it can do is teach us how fake news spreads. In a world like the one that we live in, sometimes it pays to be a little bit skeptical. I've thoroughly burnt myself out for the next month and a half, so don't expect more shenanigans from me unless I get struck by an idea with Nobel Prize winning levels of tomfoolery. Send this to some old people to keep them educated. Congrats on learning how to build a GNN. Till next time.